Hi, welcome to session 13. In this session, we will discuss about how to evaluate a classification model. In the previous session, we discussed about how to build a classification model using logistic regression. Once you build the model, how do we evaluate what metrics we have to understand how good or how bad the model is? So primarily we'll focus on creating a confusion matrix and ROC AUC and understand what information they provide from the perspective of evaluating a classification model. So for this session, I have created a folder called session 13 in the GitHub location, and I have created a classification HR attrition analysis V2 notebook. So let's open that one. You can download and open it on your Jupyter notebook session. It's called _V2, and we have already gone through the first steps of building the logistic regression model. So you understand the data set now. HR attrition. So we are solving a problem of HR attrition, and we have done some EDA. We have built a classification model with just one variable. So we'll continue with that, and we have built a logistic regression model here, which looks like the sigmoid function here, and we have predicted the probability values, and we predicted on the test data. So the model is logreg underscore v1 predict on the x test, and we have gotten what it predicts, the y prediction values. And if you remember, we have taken the threshold value of 0.5. So if the probability of y equal to 1 is more than 0.5, then we take in y equal to 1. That means the employee is going to leave. And if this value is less than 0.5, so we'll assume the y value to be 0, so the employee will not leave. And we have looked at some of the samples. For example, here we have taken some randomly 10 samples from the test data. We have about 3000 samples in the test data, and we are looking at some 10 samples here, and this is the actual value the employee has left, and the model also says that the employee will leave. So this is correct classification, but this one is a misclassification. So there are some misclassifications and some correct classifications are there by the model. And if you look at all the 3000 samples, so there is this method called accuracy score, which says how many ones that have been predicted as 1, how many zeros that have been predicted as zeros, and how many ones that have been predicted as zeros, and how many zeros that have been predicted as ones across all the 3000 samples. And the accuracy score comes out to be 0.76, 0.76. So 76% of the samples we are able to predict accurately with just one variable here, which is pretty good. But we'll take that discussion forward and understand little more deeply how to evaluate the model and why this particular accuracy score that we see here may not be very valuable. It does not contain enough information how to evaluate a classification model. So let's start with evaluating classification models. If you look at the actual and predictions, there are 4 different scenarios are there: 1 1, 1 0, 0 1, and 0 0. So how many correctly classified from the class of left y equal to 1 and how many correctly classified from the class of not left. So if you look at the 4 scenarios, actually the employee has a left, predicted as left. Actually the employee has a left and predicted as what? Not left. So this is a correct classification, but this one is a misclassification. But this misclassification has a higher cost because the employee has a left and predicted as a not left, which is the main objective of this modeling, isn't it? The main objective of building this model to identify those people who are likely to leave. But this particular scenario explains or denotes the model is not able to identify some employees who are likely to leave. So this is a very high cost, this particular failure or misclassification. The other way around, employees who are not likely to leave but the model says left, of course it also has a cost, and this is of course a misclassification, but this failure may not be as high cost to the organization as the previous one. And this is the last one, not left, employee not left, and the model also says not left. So you need to understand how many of these misclassifications are there and how many this kind of misclassifications are there. If these misclassifications are very high, then the model is of course not acceptable. Even if this misclassification is a little higher, but this is not high, then you can still go and leverage the model for deployment. So to understand all these 4 different cases, what we need to do is we can build something called a confusion matrix. So this is probably one of the most important metrics that we build in classification model. So let's first build the confusion matrix. Then we will discuss about what information it provides and how to take that information and understand how good or how bad the model is. So confusion matrix, from scikit-learn matrix, you can import confusion matrix, which is going to give you the confusion matrix, but we can also visualize it. So there is another class called confusion matrix display. We can import that as well. And to build the confusion matrix, just call confusion matrix and provide the actual values and the predicted values. So we'll give the actual ones and zeros and the corresponding predicted ones and zeros from the test data. And this is for orientation of the matrix. When we look at the matrix, we will know the class 1s will be shown as the first row and class 0 will be shown as the second row. And these are the different numbers. If you see, there are 4 different numbers which depicts these 4 different scenarios. But to understand it a little better, we can use the confusion matrix display and give this created confusion matrix here and how to specify the labels. That means the ones should be called as a left and 0 should be called as not left. So let's make it not left. And if you plot this, and this is the matrix that we get here, then which of these quadrants depicting what scenario? So what is a confusion matrix? Is an important tool for evaluating classification model because it provides a detailed breakdown of the model's performance by showing the number of correct and incorrect predictions made for each class. So if you see the confusion matrix, the row of the matrix depicts the true levels. That means out of this 3000 samples that we have total in the test data, these are the total number of people who have left. So 209 plus 541, so that's a 750. So 750 people have left and the remaining people have not left. So this row represents not left. This row represents left, the actual levels. But out of that, what is predicted by the model? So the model predicts that these are the each column represents what the model has predicted. So this is the left class. The model has predicted that these people are going to leave. And this column represents the model predicting that these people will not leave. So you can see there are 4 different classes. For example, here, if you look at, these are the 1, 1, its actual value is 1, predicted as 1. This is the actual value as 1, predicted as 0. This actual value is 0, predicted as 1. This actual value is 0, predicted as 0. So these are the correct classifications, these 2 quadrants, and these are the misclassifications. Now based on that, each of this quadrant has got a name. So what are the different names of this quadrant? Now these 2, based on the model prediction, for example, the model basically says these are the positive classes. The model says these are positive and negative classes, saying that these are the people has been identified as a positive classes by the model. What do you mean by positive classes? The model says these are the suspects, these 2 column, these 2 quadrants, which shows the employee, the suspects, the employees are going to leave because they have been predicted as going to leave. And these are the negative classes. The model says that they are not going to leave. So from the model's perspective, these are the positive cases and the negative cases. It's almost like, so when you go to a hospital for a diagnosis, right, and the diagnostic tool says it's a positive case, it's a negative case. So same thing, this model is nothing but a diagnostic tool which says these are the positive cases and these are the negative cases. But not all the cases which has been identified by the tool or the model as a positive will be actually positive. Some could be false positives as well. So now this quadrant which has been identified as a positive and they are actually positive because they are leaving. So this is called true positive. So TP stands for true positive. So these are identified as a positive cases and these are identified as a negative cases by the model. So this is correctly identified as a positive, so that's why they called true positive. So TP stands for true positives. And these ones which have been identified as a positive cases by the model predicted, wrongly predicted, so they're actually not leaving. So these are called what? False positives. FP stands for false positives. Now these are the cases which have been identified as the negative cases and wrongly identified because they're actually leaving. So this is called false negatives, FN. And this is of course true negatives. They're correctly identified as a negative. They have been identified as a negative and correctly identified as negative case. So this is called TN, which stands for true negatives. So true positive, false negative and true negatives. Now if you look at the confusion matrix again, this is simply depicting what we saw just now. So the predicted classes are shown as columns, the actuals are shown as rows, and this is true positive, false negative, and true negatives. Now In our case, the false negatives, which are identified as not left but they are actually leaving, so these are very costly. These misclassifications are very costly compared to the false positives. So what might happen is, because you have not identified these people as leaving, so the HR will never know they are going to leave, so there will be no intervention. They will only know when they leave. They will basically, submit their resignation papers, and this would actually lead to what? This might lead to higher cost in terms of impact to the projects and the cost of rehiring new employees, the project timelines, right? So there could be multiple different costs because of this failure. But this is the cases where the model says the employee is going to leave. So the HR actually make an intervention. Let's say the organization offers some benefits or compensation to the employees, but they're actually not leaving, right? So this could be also a cost, but may not be as costly as these failures. So in this particular case, we would be more concerned about the number of false negatives here. The number of false negatives are very high, then we can say the model is not good, which is the case here, because it seems to be the number of false negatives are extremely high here. So even though the model's total accuracy is about 76%, but this we are only able to identify out of 750 people who have left, only 209 we are able to identify correctly. 541 are going undetected by this particular model. So you can say the model is not that good, not very useful for deployment. In certain other cases, the false positives could be very costly. So let's look at a couple of cases here. Which failures are costly, false positives or false negatives? That depends on the problem that we are solving, the classification problem. For example, building a classification model for a loan approval, if a loan applicant applies for a loan and we have built a model to predict if the applicant is likely to default the loan or not default a loan. So let's look at the case like this. For example, we can say, rather than left and not left, in this case we'll say default or not a default, default and not default. So these are the cases where the model says the applicant will default a loan and they actually default a loan. So this is, of course, we are evaluating based on the test cases in which we already know the applicant have already defaulted, not defaulted. So these are true positives, which is good because we are able to identify the risks. What are these cases? Here, the model says the applicant is not going to default. So if the model says not going to default, let's say the bank disperses the loan, approves the loan, because the model says is not going to leave, he or she is not going to default the loan, so it actually disperses the loan amount. But the applicant actually defaults the loan. So in this case, the bank loses probably principal amount and the interest rate, both. So here, false positives denotes that the bank says the applicant is going to default, and of course we will not approve the loan, or the bank will not approve the loan, but actually the customer would not have defaulted the loan. So here, of course, we have not, or the bank has not disbursed any amount, so it's not going to lose any money, but we are losing a good customer who would not have defaulted. So this could be an opportunity cost. So maybe the interest rate that we could have earned from the customer is lost. And this is, of course, the model says not going to default. So we give the loan and they're not defaulting. These are actual customers. These are the risks that we have eliminated, but these are the risks that we could not eliminate and a very high cost. So in this case, every one failure cost us the principal amount and the interest rate. So here, every failure probably cost us an interest rate. So in this case, we will again be very concerned about if the false negatives are very, very high. Now let's look at the other case. We're building a classification model for detecting spam mails. So a classification model, when the mail arrives, a classification model will detect if it is a spam mail or not a spam. And based on that, let's say we have a inbox, right? We receive the mail. So there's an inbox and a spam box. So based on that, the model will either put the mail into the inbox or to the spam box or redirect to the spam box. So this kind of models are widespread in any emailing system, automatically detects the spam and not spam mails. Now in this case, let's say we built a model and now let's look at these cases. This is spam. This is not a spam. This is spam and not a spam. Now true positives and true negatives are correct classifications, so we are not concerned about that. We are concerned about misclassifications. So what does the false negative means here? So the model says it's not a spam, but it's actually a spam. Now because the model says not a spam, the email will appear in the inbox, but it's actually a spam mail. That's why you see a lot of spam mails in the inbox. So those are the false negatives, which is acceptable to a certain extent. But what about the false positives? The model says it's a spam. Because the model says spam, so this mail goes to the spam box. But it's actually not a spam, it's actually a good mail. So you are getting a good mail into the spam box, which is most likely not acceptable for a emailing system. So the trust of email system will diminish if you start putting a lot of this good mails into the spam box, right? So in this particular case, the false positives are extremely costly, and we need to reduce the false positives as far as possible, even at the cost of putting a lot of false negatives. That means a lot of spam mails into the actual inbox. That's why we see a lot of spam mails in the inbox, because unless the model is extremely certain, right, about the mail being spam or not a spam, it will not put that into the spam box, because there's a risk always that a good mail might go to the spam box. So this is very important for any classification model to identify which of these misclassifications are costly, and you find a model based on which minimizes either this quadrant or this quadrant. In confusion matrix, these two are kind of trade-offs. The false negatives have to be minimized. For false negatives has to be minimized, false positives may go up, or false positives has to be minimized, false negatives may go up. We'll look at that little later. Now, how to identify? Do we need to look at the quadrant? So there are different metrics measures which are defined for these kind of scenarios. The first one is total accuracy, which we saw. which basically says how many we got right across all samples. So this is almost like what are the numbers in case of true positive plus true negatives divided by all the cases, true positive, false positive, true negative, and false negative. So all the samples and how many we got right. So that's called total accuracy, which we already saw that here. So we got a total accuracy of 0.76, which is TP plus TN divided by all the quadrants. The second one is called precision. Precision is defined how many actual positives or total number of positives identified by the model. That means how many the model has identified as a positives, because these two quadrants has identified as a positives, and out of that how many are actually correct. So this is a model's precision. So how precise the model's predictions are. So this should be TP. So we got how many correct, divide by TP plus FP. How precise the model is. So in this case, it would be, my precision would be 209 divided by 209 plus 154. Whatever that number is, we'll calculate that. What's a recall score? So there is one more called a recall score, which is also known as sensitivity or true positive rate, which is how many actual positives are there. So this is calculated row wise. How many actual positives, so how many people have actually left, and out of that how many the model is able to identify. So this should be your recall, how well the model is able to recall is true positive divided by true positive plus false negative, because these are the actual positives there, the actual cases of left classes, and how many the model is able to identify. So this is going to be called a recall. So in our case it will be 209 divide by 209 plus 541. So that will be recall score. Now if you look at this, in both the formulas, the precision is TP divided by TP plus FP, whereas recall is TP divided by TP plus Fn. So if you are concerned about false negatives especially, then recall score is an important measure, because the precision does not have any information about false negatives. So if you are looking at how good the model and false negatives are important to minimize, then you look at the recall score, because as the false negatives go down, the recall score will go high, or the false negatives go high, the recall score will go down. So if you just look at the recall score, it gives you a good idea or understanding about how good the model is, from the perspective that the model should be should have very less number of false negatives. Same thing, for example, in our case, in our HR case or a lone default case, it's very important that we use a recall score to measure the accuracy of the model. Whereas the models where FPs are very important to minimize, we look at the precision. So in the spam box, spam or not a spam, because if the false positives are lesser, the precision will go very high. So in this case, the precision is very important. So all models should be driven by one single metric only. No point in measuring all possible metrics, but what metrics to measure has to be identified by first understanding what are the cases, what classification models are costly for you, and based on that you pick up the metrics. That's important. either recall or the precision. Sometimes it's not possible to kind of understand which are important. Maybe both the cases are equally important to minimize. False negatives and false positives. Both are equally costly, or we do not have sufficient information to understand which are more costly. So we can assume that both are equally costly and we want to minimize both. Then what we do is we take the harmonic mean between the precision and the recall score, which is called the F score or F1 score, and is written as 2 times the precision multiplied by recall divided by precision plus recall. If the precision is high and recall is low, F1 will be low. If the precision is low, recall is high, then also F1 will be low. Only when both are higher, then only the F1 score will be better. So the 4 important metrics, one is total accuracy, which is not very widely used. It just gives you initial indication about how good the model is, but we cannot really take that for evaluating a classification model. We will discuss something called class imbalance problem in some of the future sessions, and we can see how total accuracy can be very, very misleading in that case. So that's why total accuracy is never used or hardly used. Then precision, when false negatives are important to minimize. Recall, when false negatives are important to minimize. And then F1 score, if you want to measure and strike a good balance between false positives and false negatives. There's something called true negative rate or specificity. We'll discuss that a little later from the ROC AOC perspective. Now, how to find them? The scikit-learn has pre-built methods called precision score, recall score, F1 score, and classification report, which gives you all the scores. So you can import that. And you can see the recall score comes up to 0.27, which is very low, which makes sense here because our recall score is 209 divided by 209 plus 541 false negatives. That means if there are 100 people leaving, we can only identify 27 people. So this comes out to 0.27. We can only identify 27 of them. The remaining 73 people will go undetected by this particular model. That's why this model is not a good model at all for deployment. Precision, probably a little higher, is about 0.57, which is again 209 divided by 209 plus 154. And F1 score is, of course, the harmonic mean between these two comes out to 0.37. And you can also look at the complete report here, which normally we do that rather than looking at each individual. Classification report, we give the actual value and predicted value. Of course, that's a parameter for all the metrics. And it gives you the precision, recall, F1 score, and support. So let's look at what are these values. It gives you the precision recall score for both the classes 0 and 1. Right. So support means how many cases, test cases are there. Totally there are 3000 cases are there. You can see total. Out of that, 2250 are people not left and 750 people are left cases. And for class 1, the precision is 0.58 and recall is 0.28. That's what we measured here, 28 and 58. And the F1 score is 0.37 or 0.38. Similarly, you can also calculate the precision recall for the negative classes. We normally don't do that, but in certain cases it might be required. So for example, for positive class, for the positive class, the recall value is how many total left cases, and out of that how many we have identified. So TP divided by TP plus Fn. Similarly, we can also have a recall score for the negatives. So how many true negatives? This is for positive classes or class 1. So recall score. So out of total number of negatives, how many we able to identify correctly? That will be true negative divided by true negative plus false positive. So that's recall for the negative classes, which is also called the true negative rate or specificity. It's called specificity. The sensitivity is the recall score for the positive classes, true positive rate. Specificity is the recall score for the negative classes, true negative rates. And we can also calculate that. So recall score is 0.93, which is very high, and we can see that is very high here, because out of that 2250, so 2096 have been identified correctly. 96 plus 154. You can see this value will be very high. So this model is able to identify who are not going to leave, but not able to identify correctly who are going to leave correctly. And total accuracy is 0.76 or 0.77. That's total accuracy. You can also calculate a macro and weighted average. So this would be the average of these two, and this should be the average of these two, and this should be the average of these two. Simply the average of the precision, recall, and F1 score across all classes. Simply take an average of this. The weighted average is, we don't take simple average because there are more 0 classes than 1 classes. So this is a weighted average of across all the scores and precision. So because there are more cases here, so it's a little less weighted, and this should be we mostly use this one. This particular row is very important, especially when you're identifying a particular classification class, because most of the models are, when you say the employee is going to leave or not going to leave, so the model mostly focuses, evaluation focuses on whether the model is able to detect the people who are going to leave or not going to leave, people who are going to default or not going to default, right? The customers are going to churn or not going to churn. But it's also important that we keep track of other metrics. In certain cases, we might look at some of the scenarios in future sessions. But one important condition here when we measure all these metrics is, in this case, that we have taken the threshold value P of y equal to 1 to more than 0.5 y equal to 1 and less than 0.5 y equal to 0. So this is what we have taken as a condition to generate these numbers. But if you take a different threshold, let's say 0.4 and less than 0.4, all these numbers are going to change. How they are going to be affected, so we have to let's look at that. So without knowing the cutoff probability, can you evaluate the models? So how to evaluate and compare models? For this, we have to predict the probabilities first. So rather than predicting the classes directly by assuming the threshold to be 0.5, we are going to predict probabilities from the model. So the classification models have two functions. One is called predict. The other one is called predict underscore probability. So this is going to give you the probability values. And if you see, I'm looking only at the 5 first cases of the test cases. It gives you on 2 probability values. So this is the probability that this particular test case belongs to class 0, that is not left. and this is the probability that belongs to class 1 or left. And if you add these two, of course this will be of course 1.0. All the rows if you add, they'll amount to 1.0. So this is the probability that this employee is not going to leave, 0.85, and going to leave 0.14. So that's why this probably is identified as a class 0, not class 1, class 0. And this is also identified as a class 0, identified class 0, 0, and probably this one is identified as class 1 because this is more than 0.5. Now we don't need both the probability value. If you just know one, most likely what is the probability that somebody is going to leave or not going to leave, which is depicted by the second column. So we'll just take that column and let's add to our data frame here. So you can see this is actual 1 and predicted as 1 because this probability value is more than 0.5. This is actually 1 but predicted as 0 because the probability value is 0.35. The model predicted this employee is going to leave is 0.35, so basically it says we are not going to leave. So you can see the predicted values are derived from the probability values based on this particular condition. Now a good model, right, if you look at the probability values, a good model would mostly predict probabilities more than 0.5 for class 1. So whichever the actual class 1s, right, a good model would have predicted the probability values more than 0.5. A good model. And for the classes 0, right, it should have predicted less than 0.5. But there are certain cases of, right, incorrect cases also there. Now what I can do is, what are the predicted probabilities? What are the predicted probabilities by the model for class 1 and class 0? We can actually look at the distribution of that. So let's look at that. So I'll do a displot YDF predicted probabilities, and I will look at the actual cases. The actual cases here 0 and 1. So this is not left and this is left. The blue ones are left, these orange ones are, so blue ones are not left, orange ones are left. And you can see the predicted probability values are ranging from 0.0 to 1.0. In this case, I think most of the predicted probabilities are, the higher probabilities are about 0.6 and 0.7 only, which is fine. And you can see if you take, let's say, 0.5 as a cutoff in this case, that means some of the people who have actually left, they're depicted by this orange histogram chart, right? So there have been predicted as a less than 0.5. So those are the misclassifications here. But the blue ones are very high. That means people who have not left, the predicted probability is predicted as less than 0.5, which is good. But in this case, some of the cases, people who have not left, also the model has predicted more than 0.5. And of course, this is a good cases, right? So what you can do is you can depict that into a KD plot. So let's say this is a KD plot. And this is the histogram of, this is actually the kernel density estimation, the probability distribution of both the classes. The blue ones are not left and the orange ones are left classes. And if we take the 0.5 as a cutoff, this is taken as a cutoff probability, then we can see that the orange ones which are actual one, and this is the cases which are true positive cases, because they're actually positive and there are model has a predicted probability value more than 0.5 for that. Similarly, for the blue ones, so these blue ones, these are the true negative cases. The model has predicted probability less than 0.5 and they're actually not left cases. But the problem here is, now these blue ones that you see here, these cases are misclassifications. Similarly, these cases also misclassifications. And what are those cases? Now, these are wrongly predicted higher probability than 0.5. So wrongly identified as a positive, but they're actually negative. So these are called false positive cases. And these are the false negative cases. They're actually people left, but probability value predicted less than 0.5, hence classified as negative cases. And we can see if we change this cutoff, now let's say the cutoff goes from 0.5 to 0.6. So if you move this cutoff to the right here, what happens is the false positives would go down, but false negatives will go up. So you can see the false negatives will go up. And if we reduce the cutoff, the false negatives will go down, but the false positives will go up. That's why false positives and false negatives are trade-offs. And as we change this cutoff probabilities, we change the number of false positives and false negatives. But the question is then, if not 0.5, what is the most optimal cutoff? Because if you want a model, in our case, we want as small false negative as possible, so you can actually reduce this cutoff to much lower case. But what will happen is if you reduce, there will be a lot of false positives. That means if you look at the confusion matrix here, if you reduce the cutoff probability, let's say we say probability equal to 1, more than 0.2, then only the class is 1, and less than 0.2, the class is 0. So in this case, this will reduce significantly, the false negatives. But false positives will go up very high. So this is the case when you become risk averse. So you don't want to take any risk, right? You want to identify as many employees as possible who are likely to leave. Then what happens is you might have to compensate a lot of employees unnecessarily because they will be identified as left, but they are not going to leave. So you have to strike a balance again. So, but let's look at one of the other metrics which basically tells you how to identify that. So in this case, we look at something called ROC AUC. So one way of doing that is to kind of change your cutoff probabilities. So start with a very low cutoff probability and increase our cutoff probability slowly and slowly, and keep observing how our false positives and false negatives are changing, and which particular case of false positives and false negatives are acceptable to us, right? So what you can do is you can do that and keep observing that, and to do that we use something called ROC-AUC, which stands for Receiver Operating Characteristic Curve. It's actually a plot that illustrates the diagnostic ability of a binary classifier system as it discriminates the threshold is varied. Threshold is varied means the cutoff probabilities is changed. This method was originally developed for operators of military radar receivers. That's why the term called receiver operating characteristic, especially for the submarine. So in submarines, people, there will be operators. There will be operators which should be monitoring a radar and trying to identify if the approaching object is another submarine or maybe not a submarine, right? So based on that, they're basically evaluated how good an operator is. So that's where ROC, the concept of ROC AUC comes, and which is used in this particular case as well. Now, if you look at this particular distribution, right, the predicted probabilities, because the predicted probabilities, the curves are overlapping, right? That's why there's a lot of misclassifications here. So now let's assume that if my probability distributions would have looked something like this. Let's make an assumption. Let's say this is the predicted probability which comes from 0.0 to 1.0. And let's say for all my negative classes, the predicted probabilities, let's call it 0.5. The predicted probabilities are, the distribution looks like this. Whereas the predicted probability for the positives look like this. So these are negatives and these are positives. So in this case, there is no overlap between the predicted probabilities or very minimum overlap. And when you take a cutoff at 0.5, right, so you can classify everything correctly. So the false positives and false negatives will be not there, very, very minimum. So this is of course the case of an ideal model, a perfect model, which is typically not possible in the real world. There will be some overlap. But instead, let's say we get a model something like this, where the predicted probability for the negative classes looks something like this, and for the positive classes looks something like this, right? And this is about cutoff probability 0.5. So here, of course, there is some overlap between these two, but the overlaps are very minimal. Okay, mostly you can identify the true negatives and true positives correctly. So this is a good model where the overlap is very low. But of course, if you look at a model where the predicted probability for the negatives looks like this and the positives looks like this, that means there's a lot of overlap area. So this is a classic case of a bad model or not a good model. So if you just measure the area here, right, if the overlap area is very minimum, that's a good model. Overlap area is very high, then it's a bad model. So ROC AUC curve gives you some indication about that. So let's look at that. ROC AUC curve is actually between true positive rate, which is our recall score, and false positive rate, which is 1 minus of true negative rate. So true positive rate is what? As we have already seen, true positive rate is Tp divided Tp plus Fn. True negative rate Tn divided by Fp plus Tn. So in this case, true positive rate equal to Tp divided by Tp plus Fn, and false positive rate is 1 minus of true negative rate, which is 1 minus of Tn divided by Tn plus Fp. Okay, which comes out to be, if you look at do this, so Fp divided by Tn plus Fp. So in a way, it says how many true positives and how many false positives. So what happens if we change the cutoff probability? What happens if we cutoff probability is 0.0? So let's look at in this particular case, if we take the cutoff probability to be 0.0, then what will happen? So in that case, I cannot identify any negatives. All the true positives should be identified correctly. So there won't be any false negative. But all my true negatives will be wrongly classified. Okay. So my false positives will be very, very high. Right? Because everything is identified as a positive. My false negative will be extremely low, minimum 0. Isn't it? So in that case, what will happen is, if you look at here, all my true positive rates, everything will be identified as a true positive rate. So this is the case, this particular point is the case of cutoff probability 0.0, because all my true positives will be identified. So if you see the scale is 0 to 1, the true positive rate will be 1, and my false positive will also be 1, because my false positives will be very, very high, right? Because true negatives cannot be identified. So 1 minus true negative rate. So none of the true negatives will be identified with 0. So 1 minus 0 will be again 1. And what happens if the cutoff probability is 1? Now if you go to the other extreme and basically say my cutoff probability is 1, then in that case my false negatives will be very high and false positives will be very low, because none of them will be identified as a positives, right? All the true negatives will be identified correctly and true positives will not be any. So there won't be any true positives there, because none of the predicted probability will be more than 1. So I cannot identify anything as a true positive. So true positive rate will become 0. So this is the case of cutoff probability 1. This is the case of cutoff probability 0.0. So here I cannot identify any positives, and 1 minus true negative rate, my true negatives will be identified everything. So 1 minus 1 will be 0. So this is the case of cutoff probability 1. So very important to understand that, right? In all cases, when you take a cutoff probability as 0.0, this will be the case, and cutoff probability 1, this will be the case. And when we move from cutoff probability 0.0 to 1.0, that means we take a cutoff probability of 0.1, 0.2, 0.3, slowly move it, right? So in this particular curve, as we go from cutoff probability 0.0, 0.2, 0.3 and so on and so forth, you can see my true positives are getting smaller and true negatives are increasing. So true positives are reducing and true negatives are increasing, right? So the curve will look something like this. So these are the different cases. So let's say this is a particular case. We've taken a cutoff probability where the true positive rates have reduced, but negative rates have increased. Now this is another case of cutoff probability. Similarly, if we go from 0.0 to 1.0, for every small steps, right? 0.0.1. So this will actually look like this. Okay. Not necessarily for every model. Some model it will look like this, and some model it will basically look like this. So this curve belongs to the cases where the overlap between the models predicted probability is very high, and this is the one when the overlap is very, very small. right? So now just take one ideal scenario that we discussed already, that when we change from 0.0 to 1.0, so let's say this is the case where the predicted probability for all the negative classes are less than 0.5, whereas the predicted probability for all the positive classes are more than 0.5. That means there is a cutoff probability here where all the true negatives and true positives are identified correctly. So true positives are 1 and true negatives are 100%. So your true positive rate will be 1 and true negative rate will also be 1. So true positive rate 1 is what? This point. And true negative rate is also 1. So 1 minus 1 is 0. So this particular point. So this is the case. This is the point which would be identified for a perfect model. So when you go from the 0.0 cutoff to lose a 0.5 cutoff, so this is how the curve will look like. So this curve belongs to a perfect model, which is of course not possible in a real world scenario. This is a perfect model. And as and when this predicted probabilities start overlapping, right? Start overlapping between the negative classes and the positive classes, and more overlap are there, right? So this particular curve will start detracting towards the diagonal. And when there's a perfect overlap, that means the predicted probabilities for true positive and true negatives cannot be distinguishable at all. That means we cannot find out which is positive and which is negative. So that line will be the diagonal line, which is called a random classifier. That means the classifier do not have an ability to classify. And as and when the overlap area is becoming smaller and smaller, it will go towards this perfect classifier. So this is the ROC AUC curve, the diagonal line for the worst one, worst, and this is the best. And our model is somewhere, typically real world model will be somewhere in between. So to understand what is a good model, what we do is we look at this area under this curve. So when this particular model touches this point, so that will be the area what this area, this side is 1, this side is 1. The total area under the curve will be 1.0. So the AOC is, ROC AOC is 1.0, that means it's a perfect model. The worst one will be what? The half of this particular square, that's 0.5. So worst model is 0.5. So ROC AOC varies from 0.5 to 1.0. And the closer to 1.0 is the best model, better model. The closer to 0.5 is the worst model. And we can actually measure that here. So the perfect model, no false positives or negatives. An average model, some false positives and some negatives. Worst model, very high false negatives. It's called random model. We're not able to identify which is positive and negative. A lot of overlap are there. So area under the curve is 1.0 for a perfect model. Area under the curve typically lies between 0.5 to 1.0. And if it's 0.5, then it's a random model or worst model. So let's go and look at the display. So from scikit-learn, ROC AOC score and ROC AOC display. And we can actually look at the score here. But for the score, we need to pass the actual value 0 and 1 and the probability values, because he's going to find out the false positives and false negatives for every cutoff value. It comes out to 0.77. And let's look at the curve. Yeah, this is the curve that we get. We don't need to do it out. Yeah. So this is a true positive rate and this is a true negative rate. And this is the area, and this is the for the cutoff probability of 0.0. This is the cutoff probability for 1.0, right? And as we change the cutoff probability, you can see the positives and negatives are changing. Okay, this of course will not be very smooth as we shown here in the diagram. There will be some variation should be there. And what happens if we change the cutoff now? For example, rather than 0.5, so here 0.7 means it's good model, average model, not a good model. Now changing the cutoff probabilities. So now what we'll do is we will change the cutoff and see what happens. So rather than saying the probability of y equal to 1 is more than 0.5, it's y equal to 1, less than 0.5, y equal to 0. We'll change that and see. Let's make it, what if it's more than 0.55 or y equal to is more than 0.35. Two cases I've taken here, and see how the false positives and false negatives are changing. For that we have to explicitly define classes. So we'll take the predicted probabilities and say if the probability value is more than 0.55, we'll say it's class 1 or class 0. So that will get my new predictions, and we'll build a confusion matrix between the actual and the new predictions based on now a different cutoff, which is 0.55 here, and look at the confusion matrix. And if you see here, my false negatives have a little gone down here now. And if you see here now, compared to the previous one, sorry, false negatives have increased because we are going to the right, correct. And my false positives has gone down from 154 and 541. It's gone to 88 and 546. So we have increased that cutoff probability here. That means we have gone to the right here, right? So my false positives have reduced, but my false negatives have increased by this much. These are my false negatives. Similarly, if I now reduce the cutoff probability to 0.35, less than 0.5, and you can see my, in this case my false negatives have gone down and false positives have increased, because I have gone to the left now, so my false positives have increased and false negatives have reduced. So these are my false positives. These are my false positives. And these are my false negatives. So you can see that the confusion matrix is not fixed for a particular model. This changes based on the cutoff probability, what cutoff probability we take, right? So it basically keeps changing. But what is the optimal cutoff probability? That depends on how much false negatives and how many false positives you want. But there is a specific approach called cost-based optimal cutoff, optimal threshold. We'll look at that in one of the future sessions when we look at a specific problem where the cost of each failure is mentioned or specified. That becomes a little easier to find the optimal cutoff probability. But here the whole point is the ROC AUC depicts the ability of a model to distinguish the positives from the negatives, which basically shows that the amount of overlapping and non-overlapping area between these two curves. Okay, so the more and more overlap, the ROC AUC will become smaller and smaller. Basically says that the model do not have the ability to distinguish or discriminate between the classes, but the area becomes higher and higher and looks something like this. That means it says the model has a very good ability to distinguish between these two classes, what is positive and what is negative. And as we change the cutoff now based on the cost of failures between false, positive, negative, we can change the cutoff probabilities and we can derive the expected number of failures that we can withstand and for the model to be deployed in the real production. This is of course a building classification report based on the new predictions, and you can see here my recall scores have been increased from 0.27 to 0.50 now when my cutoff probabilities are reduced. So this brings us to the complete evaluation of classification models, a comprehensive evaluation. It's very important that we understand all these concepts very clearly. What are the true positives, what are the true negatives, false positives and false negatives, and what are different metrics and which metrics is important in what scenario based on false negatives are costly for you or false positives are costly for you. And we cannot really evaluate a model based on the confusion matrix initially because we may not have the appropriate cutoff probability. So look at the ROC, AOC and understand how well the model able to distinguish between the positive and the negative classes. So that brings us to the end of the session. So here's an exercise that you can build a logistic regression model with all the variables, because this we have built with only satisfaction level, but we have a significant number of variables here. Class evaluation, number of projects, average monthly hours, so on and so forth. This is of course why. So you can do encoding of categorical variables, one encoding department salary, and then build a model and see how we can improve the accuracy of this model. Then compute ROC, AOC and draw the curve, and compute the confusion matrix and draw the confusion matrix. This is of course either you can do it for the cutoff probability 0.5, or you can also experiment with different cutoff probabilities and see the false negatives and false positives and create a confusion matrix. So thank you. So this is a very important session because evaluating classification models are much more complex compared to evaluating regression models, and I hope you can go through and understand these concepts very deeply, and I'll address some more classification models in the future session.